The next pollutant is carbon monoxide or CO. CO is harmful when breathed. The CO emission from internal combustion engines are controlled by the relative air-fuel ratio or the fuel equivalent ratio. The figure on the left side is showing the variation of SI engine CO emission as a function of air-fuel ratio for 11 different fuel. Each fuel has its own HC ratio, which means that these 11 different fuel have a different stoichiometric air-fuel ratio. As you can see on this figure, each fuel has its own line. And then the figure on the right side is when we plot the CO emission as a function of the relative air-fuel ratio or lambda. So you can see in here that all 11 lines combine nicely into a single line, which means that the CO emission is a function of the relative air-fuel ratio lambda or the fuel equivalent ratio phi. For the spark ignition engines that operate close to the stoichiometric at part load, and then depending on the calibration, maybe fuel rich at high load, the CO emissions are significant and need to be controlled. For the diesel, it's always operate well on the lean side of the stoichiometric mixture. The CO emission is low. Okay, therefore it is unimportant in diesel engines. And then the level of CO observed in spark ignition exhaust gases are lower than the maximum value measured within the combustion chamber, but they are significantly higher than equilibrium value in the exhaust condition. What does mean here? That the processes which govern the CO exhaust levels are kinetically controlled. So it means it is controlled by the rate of the chemical process. In a premixed hydrocarbon-air flame, the CO concentration is maximum in the flame zone, and equation 11.21 is showing the path for the formation of CO. So it starts with RH, so this one is the hydrocarbon fuel, and then there will be an abstraction of single H by oxygen, and then we have only R here, so it means this is the hydrocarbon fuel minus one single atom of H, and then there will be a reaction with O2 to form RO2, and then following this path, and at the end we have the CO formation. So R here stands for the hydrocarbon radicals. Once again, this is the hydrocarbon fuel less one single atom of hydrogen. And then the CO is then oxidized to CO2 at a slower rate following equation 11.22. Okay, CO react with OH to produce CO2 and single H. CO concentration in the immediate post-flame burn gases are close to equilibrium. Next one is unburned hydrocarbon or UHC. UHCs are the consequence of incomplete combustion of the hydrocarbon fuel. We have UHC between 1 to 2% of the fuel for gasoline. Actually, it can be higher than 2%, especially if we have EGR inside the engine. It is much less for the diesel combustion. The levels of this UHC are expressed in ppm, part per million, in terms of the C1. And then engine exhaust gases contain a wide variety of hydrocarbon compound. You can see on the table here that for the first row here is the composition for the engine out emission. It has around 33% of paraffin type hydrocarbon, and then 27% olefin, 8% acetylene, and 32% aromatic. And then at the catalyst out location, we have a high paraffin percentage here, 57, and then 15% for olefin, 2% acetylene, and 26% for aromatic. Flame quenching could result in unburned hydrocarbons emission. Flame quenching or extension occurs at the walls of the engine combustion chamber, and this is due to lower temperature of the wall, and these cool walls acts as a sink for the thermal energy and the reactive radical species generated within the flame. And then quenching can occur under several different geometrical configurations. And one of this flame quenching occurs when the mixture or the flame try to enter the crevice zone. Then there might be a flame quenching at the entrance of this crevice zone. When the flame quenches, it leaves a thin layer or volume of unburned mixture ahead of the flame. This feature helps us to identify the source of hydrocarbon emission. There will be absorption and desorption of hydrocarbon by deposits and then by lubricating oil. And then there will be a flame quenching. So at this crevice, so between the piston liner and the top rings, and then flame quenching in this cascade crevice, flame quenching on the wall, flame quenching at the spark plug thread crevice, and we also have crevice in this valve seat that will result in the flame quenching as well. There will be also a bulk quenching within the flame front for lean or dilute mixture and high turbulent combustion condition. The unburned fuel that is stored inside the crevice zone will exit the zone during the expansion stroke when the chamber pressure decreases, and this unburned fuel will diffuse into and mix with the hot burn gas, and then depending on the temperature level of the burn gas, some of this unburned hydrocarbon might be oxidized, and this table is showing the processes by which this unburned hydrocarbon can be oxidized and then exit the cylinder. So we have outflow of the unburned fuel mixture from a crevice volume and then mixing with the burn gas, and some of this crevice hydrocarbon will oxidize. And then there will be a diffusion of hydrocarbon vapor out of the oil layer and deposits into the burn gas, and some of this hydrocarbon will oxidize as well. And then mixing of wall and bulk quenched gases with burn gas, some of this will also oxidize. And then exhaust blow down process will carry a fraction of the in-cylinder unburned hydrocarbon into the exhaust. And the next one will be due to the displacement of the exhaust gas by the piston during the exhaust stroke. And at the end, the unburned hydrocarbon will exit the cylinder and it will mix with the hot exhaust gas, and a fraction of this hydrocarbon will oxidize in the exhaust port and manifold. So this is outside of the in-cylinder chamber. This picture is showing the various steps in the overall spark ignition engine hydrocarbon formation mechanism. At the top here we have the hydrocarbon sources coming from the crevices, and then wall of quenching, and then liquid fuel. This unburned hydrocarbon will mix with the burn gas in the post-combustion period. Some of this will be oxidized and will go to this road. The rest will exit the engine, so during the blowdown process and the exhaust stroke process, some of this unburned fuel will be inside the residual gas, so it will go to the second cycle of the engine, and then this is what is coming out of the engine, so or will go to the exhaust pipe. The Hc concentration in the exhaust gases vary significantly during the exhaust process. This figure is showing the schematic of in-cylinder flow processes by which hydrocarbons post-combustion diffuse from the various sources into the bulk burn gases and are entrained into the blow-down exhaust gas. The picture on the left side here is showing the process during the blow-down exhaust flow. As you can see in here that the unburned hydrocarbon that is attached to the wall diffuse and then mix with the burn gas exiting this in-cylinder chamber during the blow-down process. And the feature on the middle here is during the exhaust stroke. You can see additional unburned hydrocarbon emission source here due to the hydrocarbon scrapped by the piston movement here. And this one is during the end of the exhaust stroke process. How about the unburned hydrocarbon in the GDI engines? The behavior of the liquid fuel injected into the cylinder has several HC emission impacts. Compared to PFI, port fuel injection, there will be much more liquid fuel within the cylinder, especially with a cold engine and during warm-up operating condition. In PFI system, significantly more fuel must be injected than enter the cylinder during the first several cycles. This is because some of the fuel will remain in the intake port, so we need to compensate it by having more injected fuel. For the DI, we don't need to do that because DI can have the fuel amount as needed by the engine. So DI fuel injection has the potential for reducing the cold engine fuel enrichment required. Thus, engine out hydrocarbon emission during this phase of the engine operation can be reduced. For homogeneous DI spark ignition engine under quasi-steady operating condition with gasoline, the HC emission mechanism are essentially the same as with the PFI engines. Stratified DI engines usually have a higher HC emission compared to homogeneous DI engine, and this is because of the flame quenching near the outer boundary of the close to stoichiometric fuel that occurs due to the very lean mixture. This will reduce the potential for post-flame oxidation. Also, the exhaust gas temperatures are lower, so after burning of HC in the exhaust pot is reduced as well. For the compression ignition engine case, the diesel fuel contains hydrocarbon compound with a higher molecular weights and hence higher boiling points than gasoline. There are two primary paths by which hydrocarbon can escape this diesel combustion process. First is that the fuel-air mixture can become too lean to auto-ignite, or it can become too rich to ignite. So when we have these two conditions, the fuel can still be consumed, but by a slower thermal oxidation, and it will result in unconsumed fuel at the end. This feature and the one in the next slide is showing the schematic representation of the diesel HC formation mechanism that help us to identify its several components. And this is during the ignition, delay, and premixed burn period. We have a rich mixture inside the spray, okay, this one. And then we have a very lean mixture surrounding the spray. And this one is also the source of the hydrocarbon. And then at some point we have a phi equal to 1. So it is somewhere inside this blue color region. So this is where we'll have the flame front. Okay. And this one is the schematic during mixing control combustion period. we have burn gases that diffuse outward, okay, this one, and some of the hydrocarbon will be formed in this zone, and then we have reacted a very rich mixture, so this will be also the source of the hydrocarbon emission along with other emission that we will discuss later. This is soot. Hydrocarbon emission levels from diesels vary widely with engine operating condition. We have a high HC emission during engine idling and light load operating condition. And then if the engine is overfueled, this HC emission increase very substantially. Overmixing or overleaning is an important source of HC emission. This happens especially under light load operating condition. And then under mixing, resulting in over-rich mixture during the combustion period, this is also the source of the HC emission. So this is the mechanism by which some of the fuel remaining in the injector nozzle sac volume escapes the combustion and is also the cause of the high HC emission during overfueling. The feature on the right side here is showing the effect of nozzle sac volume on the exhaust HC concentration. As you can see in here that the HC emission increases with the increase of the nozzle sac volume. The feature on the left side is showing the schematic of a different sac volume size. So let me put a green line. This is what it's called sac volume. Okay, this one has a smaller sac volume, and this one has almost no sac volume. It has a very small sac volume, but it is covered by the valve, so we can say it has a zero sac volume for the feature on the right side here. The next pollutant is particulate. Particulate emissions have long been an issue with diesel engines. Soot is formed within the evolving fuel spray, although the majority of the soot is oxidized inside the in-cylinder. A portion of it doesn't and is exhausted. Then, in the exhaust and during dispersion of gases exiting the exhaust pipe, the gases cool, nucleate condense, and form a small particle. And then as a higher molecular weight hydrocarbons continue to condense, they are absorbed into this soot particle and it will form a size distribution of the particle. For the PFI gasoline engine, usually they have much lower particulate emission than a diesel. It is by a factor of 70. However, the DI, so the GDI, has much higher particulate emission than PFI gasoline engine. So this is by a factor of 10. Particulate trap located in the exhaust system of a diesel or a GDI engine have been developed, and it is used to reduce the particulate emission, but over time there will be an increase of the pressure across this particulate trap, and it required a regeneration to burn up this trapped particle. For the spark ignition engine, the particulate emission consists of inorganic particles, of which lead compounds used to dominate, and then organic particulates, including soot, and the last one is sulfates. Depending on the sulfur content in the fuel, significant sulfate emissions can occur with oxidation catalyst equipped engine. As I mentioned to you in the previous slide, that GDI has much higher particulate emission than PFI. It is by a factor of 10. And then the role of ethanol, so for example like E10, so ethanol reduces soot formation. And we have a high particulate emission when the engine is operated during and after engine startup. For the diesel engines, particulates consist principally of combustion-generated carbonaceous material or soot on which organic compound in the exhaust gases have been absorbed. For the measurement technique, we can use a simple smoke meter or using a advanced system using a dilution tunnel. The unit of this particulate can be grams per kilogram for a vehicle, or gram per kilowatt hour for an engine, or gram per kilogram of fuel, or milligram per cubic meter of exhaust at the standard condition. The feature on the left side is a well-known feature that helps us to illustrate the critical soot forming processes and the regions where PAH, so this is the precursor for the soot, and the soot itself form in an individual diesel fuel spray during ignition delay and then premix rapid phase and the mixing control combustion phase. So we have PAH here as the precursor, and then we have the soot formation close to the tips of the spray, and this one is another spray formation as the fuel spray develop, and this is during the mixing control. We have a high soot formation at the middle or at the central zone of this spray, and then we also have the soot formation surrounding this high soot formation, and then at the very of this spray there will be a soot oxidation, so somewhere here. And then the feature on the right side is showing the sequence of chemical reaction that occurs during the fuel spray development, combustion, and then fuel reaction, and the soot formation and oxidation. So on the middle here we have the soot formation. So the soot is formed here during the combustion process, and then the majority of this soot will be oxidized, and then the net between the soot formation and the soot oxidation will be the soot production here, and then this soot production will exit the engine as the soot emission. The feature on the right side here is showing the schematic for the soot formation. It is initiated by the particle formation, where the first condensed phase material arises from the fuel molecules via their partial oxidation and or pyrolysis product. So the precursor here is PAH or polycyclic aromatic hydrocarbon, or C2H2, which is acetylene. And then we also have a particle grow, which include both a surface grow and then coagulation and the aggregation. This feature is showing the schematic of soot oxidation, and this oxidation process occurs in the overall soot formation process. So we have soot oxidation process during nucleation, and then during the surface grow, as well as during agglomeration process. And the feature on the left bottom side here is showing the impact of the oxygen partial pressure to the carbonaceous rate, which is the rate of the oxidation. As you can see on this feature, that the soot oxidation increases with the increase of the oxygen contents, and this soot oxidation process is maximum at the temperature around 2000 when we have oxygen partial pressure of 0.1, and it's increased slightly as the temperature is above 2000 Kelvin. And then in the exhaust system, we have absorption and condensation. In this case, the exhaust gas is dilute and cooled by mixing with air. So in the standard particulate mass emission measurement process, this occurs in a dilution tunnel, which simulates appropriately the actual atmospheric dilution process.